podcast, Closed Hydrogen Cycle, Innovations and Challenges in Recycling. Hello. In today's episode, we'll take a look at advanced hydrogen recovery and recycling methods that have the potential to revolutionize the energy industry. Advanced hydrogen recovery methods. The role of hydrogen as a fuel of the future cannot be overestimated, and it already plays a key role in achieving global climate and energy goals. Let us now discuss two advanced hydrogen recovery methods that significantly impact the possibilities of using this clean fuel on a larger scale. Water electrolysis is one of the most promising methods for producing clean hydrogen. It uses electricity to split water molecules into hydrogen and oxygen. Modern electrolyzers, such as those with a proton exchange membrane, PEM, are extremely energy efficient and can operate over a wide range of pressures and temperatures. For example, the Hydrogen Valley project in Denmark integrates PEM electrolysis with local renewable energy sources, such as wind, to produce hydrogen without carbon dioxide emissions, with minimal operating costs. One practical application of water electrolysis is its integration with renewable energy sources to create energy storage systems. When renewable energy production exceeds current demand, the surplus can be used to produce hydrogen. This can then be stored and used during periods of lower energy production or higher demand. Thermochemical water splitting is another innovative technology that uses heat energy to split water into hydrogen and oxygen. Projects such as the one led by the Fraunhofer Institute in Germany show how high temperatures generated by concentrating solar energy can split water efficiently, eliminating the need for electricity. The Institute is researching how to use solar mirrors to focus sunlight on a single point to achieve the temperatures necessary to initiate chemical reactions that decompose water. An example of the application of this technology is solar thermal installations in regions with high solar radiation, where local energy sources can be maximally used to produce hydrogen. This is particularly interesting in the context of heavy industries, which can use hydrogen as a power source in high-energy processes such as steel or cement production, instead of relying on traditional fossil fuels. Both technologies not only demonstrate the potential of hydrogen as an energy carrier of the future, but also demonstrate how innovation can lead to more sustainable and efficient energy systems. By pushing the boundaries of technology, we can gradually transform our society towards greater sustainability. Innovations in hydrogen recycling. Hydrogen recycling is becoming an increasingly important part of the industry's sustainable development strategy, especially in the context of growing global energy and ecological needs. In sectors such as refining, petrochemicals and steel production, where hydrogen is widely used, the possibility of its recovery and reuse opens the way to significant savings, both economic and environmental. Pressure swing adsorption, PSA, technology is one of the most effective ways to recover hydrogen. This method uses variable pressures in an adsorbent chamber to selectively bind hydrogen and separate it from other gases such as methane or carbon monoxide, often present in processed gases. This allows for the recovery of high-purity hydrogen, which can be reused in industrial processes or as a fuel for fuel cells. PSA application examples. One of the most well-known examples of this technology is its integration into oil refineries, where hydrogen is a key factor in processes such as hydrocracking and removing sulfur from fuels. Companies such as Shell and BP have invested significantly in the development and implementation of PSA systems to maximize the efficiency of hydrogen use, which helps reduce their overall carbon emissions. U.S. Department of Energy initiatives. In the United States, the Department of Energy, DOE, has programs to support the development of technologies that enable hydrogen recycling. For example, the Advanced Research Projects Agency Energy, ARPA-E project, is funding innovations to improve the efficiency and reduce the cost of hydrogen recovery processes, including advanced adsorption materials and new membrane technologies. Industrial closed loops. More and more industrial companies are considering implementing hydrogen cycling systems, where the same hydrogen is reused in different processes. For example, in the steel industry, where hydrogen can be used to reduce iron ore and then recovered from waste gases and reused. Such practices not only reduce the need for fresh hydrogen, but also significantly reduce operating costs and environmental impact. Conclusions. Hydrogen recycling in industry is becoming increasingly widespread and is a key element of sustainable development strategies. The development and implementation of advanced technologies such as PSA and government support, such as DOE initiatives, are essential to achieving these goals. These innovations open up new opportunities for industry to minimize waste and increase energy efficiency, which are key to the future of sustainable development of the global economy. Technological and economic challenges. While hydrogen and fuel cell technologies offer promising solutions for the energy future, their large-scale implementation faces significant technological and economic challenges. Understanding these challenges is crucial to effectively addressing the obstacles to a sustainable future. High initial costs. The first and one of the biggest challenges is the cost associated with the initial installation of water electrolysis systems and construction infrastructure necessary for efficient hydrogen recycling. Modern electrolyzers, especially those based on PEM, proton exchange membrane technology, are expensive to manufacture due to the use of expensive materials such as platinum as catalysts. In addition, the infrastructure for storing and distributing hydrogen must meet high safety and efficiency standards, which further increases costs. Complexity of scaling. Scaling electrolysis technology to industrial levels is not only expensive, but also technologically complex. It requires the development of large and efficient plants that can produce sufficient quantities of hydrogen to meet the needs of the industry. Scaling also requires sophisticated logistics and management systems that can efficiently distribute hydrogen to various points of use, both locally and globally. Investment challenges. Significant investment from both public and private sources is needed to overcome these barriers. Governments in many countries are already introducing financial incentives, subsidies, and tax breaks for companies investing in hydrogen technologies. However, for many companies, upfront investment remains a challenge, requiring well-thought-out financial strategies and often cross-sector collaboration. Integration with existing energy systems. The final challenge is the integration of hydrogen systems with existing energy infrastructure. This requires not only investment in new infrastructure, but also the deliberate adaptation of existing energy and industrial networks so that they can efficiently use hydrogen as an energy carrier. In summary, overcoming the technological and economic challenges associated with implementing efficient hydrogen recovery systems is key to a sustainable energy future. This requires a concerted effort by governments, businesses, and research institutions to jointly develop technologies, reduce costs, and integrate innovations at a scale that will enable widespread use of hydrogen in the global economy. Future perspectives for hydrogen recycling. Despite the challenges that remain in the development of hydrogen recycling technology, the future of this technology looks bright. As the world strives to meet international climate agreements and achieve sustainable development goals, hydrogen can play a key role in the energy transformation of our planet. Growing demand for sustainable technologies. Growing environmental awareness among consumers, corporations, and governments is driving more investment into clean technologies such as hydrogen recycling. This is seen not only as a way to reduce harmful gas emissions, but also as an opportunity to increase energy efficiency and reduce operating costs in many sectors. A key element of the green economy. Hydrogen is an extremely versatile energy carrier. It can be used in transport, energy production, and heavy industry such as steel and cement production. Its ability to store energy from renewable sources and its potential for mobile and stationary applications make hydrogen an ideal candidate to be the foundation of the green economy. Examples of innovation and adoption. We're already seeing various sectors adopt hydrogen technologies around the world, from fleets of delivery vehicles in Europe to the design of zero-emission ships in Norway, to large-scale electrolyzer installations in Australia and the Middle East that aim to produce green hydrogen on a mass scale. Long-term perspective, although technological and economic hurdles remain challenging, progress in research and the development of new materials and technologies, such as advanced electrolyzers and new recycling methods, shows that hydrogen has the potential to revolutionize our approach to energy and the environment. In conclusion, the future of hydrogen recycling looks promising with its potential to promote sustainable development and support the global economy in its transition to green technologies. Our task now is to focus on overcoming existing barriers to fully exploit the potential that hydrogen offers for a sustainable future. End. Thank you for joining us today, and I hope our episode today has shed some light on fuel cells and their role in a sustainable future for logistics. We invite you to continue exploring this topic and join the conversation about the future that awaits us all. See you in the next episode. Funded by the EU. The views and opinions expressed are solely those of the authors and do not necessarily reflect the views and opinions of the European Union or the European Education and Culture Executive Agency, ERCA. Neither the European Union nor the ERCA are responsible for them. All results developed within the project, professionals and their skills in hydrogen are made available under open licenses, CC by SA 4.0 deed. They can be used free of charge and without restrictions. Copying or processing these materials in whole or in part without the author's consent is prohibited. In the case of using the results, it is necessary to indicate the source of financing and its authors.